Hello, statics class. This is our third equilibrium analysis example on the 12th of February 2019. And we have another rod and pin type assembly. So here's our given. We have two rods and they're each of length L. They're pinned together up here at point A with a pin, so this can exert forces in the X and the Y, but it won't sustain any moment. We have a box B, which is touching the rods just at the points of the box, and the angle between the rod and the center line is theta. So the question says the box has a width of L over 2. So we know something about the geometry, and we're assuming the box doesn't move and it doesn't deform. Everything's a rigid body. This is statics. Rod length is L, just like it shows in the figure, and it has a mass M. They're uniform density, and there's no friction. So uniform density means that their weight, so mg, the weight is going to act at the center of mass, which is going to be L over 2. There's no friction, so that means the box can only exert a force perpendicular to those corners, which, given that it's a point, that's going to end up being pretty much perpendicular to whatever direction the rod is leaning. So it can be just about in any direction, so it'll be dependent on theta as well. No forces tangent or parallel to the rod surface. We would need friction to do that as it scrapes along. So using that, we can start assembling some free body diagrams and relating weight to angle and keeping everything in equilibrium. And this time, again, we're going to need multiple free body diagrams, and we're going to end up, I believe, drawing a free body diagram of the pin, which is going to be an important consideration we'll use later on for frames and trusses. So we'll start with the rod on the right. It's symmetric, on the left. It's symmetric. We could have started with any of them, and not surprisingly, this is a bit of a geometry chase, but it's good practice. So if we look at the rod being held up with pin A, and here's a little miniature of the corner of the box here, and this dotted line is the center line of the figure. So since the entire width of the box was L over 2, this is half the box width from the corner to the center line, so that's L over 4. And so we have the center of mass of the rod. And so our first force is the weight, mg, hanging down. And of course it makes an angle of phi with the rod, just like the center line of the figure does. We have a presumably upward acting force ay, horizontal force AX. Now this is the force of the pin on the rod. So the pin is pushing up and to the right. So obviously if we were to draw a free body diagram of the pin later on, if we were to happen to need that or to use it as a check, of course it would be experiencing an equal and opposite force from the rod, so it would feel the rod pushing down and to the left. So just a reminder. And then we see L over 2 here, this distance along the length of the rod to the point where we're going to apply the weight. So this is just a general sketch. So crux, sort of a crux to the solution is an assumption about the direction of the normal force from this corner. So because we've got a point and we've got a rigid surface, we can assume that the force exerted by that box corner on the rod, because this isn't really a total free body diagram here because I haven't shown a force coming from the box. I still have to do that. So I've kind of gotten this over here. I cheated a little bit. So these two together make an FBD. So I have to say that the force from the box corner onto the rod is always going to be perpendicular to the rod's surface. And that's important, is the direction of that normal force. So I have it drawn here perpendicular. That perpendicularity gives me a direction, and it gives me a direction relative to the center line, links me into the rest of the geometry, and most important, it gives me a direction and a point of application relative to the pin. Now I can start summing the moments around that pin and I know how to apply B, which is the normal force coming from the box, and then I already know the weight, and if I sum the moments around pin A, I can get B in terms of the weight, because the geometry of the normal incidence plus the location of that corner with phi, I have that expressed here as x. This came out of the geometry of the problem. So I should be able to use the sum of the moments around A to get B, given that I know it's acting perpendicular to the rod, and I have enough geometry to relate its application position x to position A. Okay, we are back with equilibrium analysis example number 3, and that was the pinned 2 rods over box B. And I've moved the screen over to show the rest of my calcs. So having established that the normal force of the box on the rod is going to be acting perpendicular to the rod surface, I was able to use the geometry of the problem to find the point of application of that normal force. Now I have an input into the sum of the moments around point A, which is this point right here, of the force coming from the box onto the rod. And so this gives me a value for B. I'm able to do the sum of the moments around around A is 0. So here's my weight. So it's acting downwards, and so the perpendicular component of that is sine phi. It's acting at L over 2. So that's the moment about point A due to my weight. And then because B is automatically acting perpendicular to the rod, I've established that. I don't have any cosine or sine function there. And then x is the distance along the rod from point A that it's acting, and that's L over 4 times 1 over sine phi, and that just came from the geometry of the problem. So now I can solve for B in terms of the variables that were given for the problem, which is what was asked for. So I can also notice that the vertical component of B is the only force that's offsetting the weight for both of the rods. There's really nothing else. They're literally kind of draped over that box. So you've got their weight being opposed by the normal force of the box. So I can set that up for the whole problem. So I can draw a free body diagram just showing the forces on the 2 pinned rods. So I have another FBD right here. I took the 2 rods and pinned them together, and then I did an FBD of the pinned assembly. You see, there's not a box. I'm just showing the force of the box in the y direction only. So this is even a partial FBD. It doesn't show the x forces per se. On the other hand, it's effectively showing that there's not much to consider in terms of the x forces. You would have to actually take the pin apart to show that. So this is all that's happening external to this pinned assembly. You have its weight dragging it down, you have the box pushing it up. There are no externally applied x forces that are not that you can show that are not opposed by the pin. I could show them pointing in opposite directions here, and they're equal and opposite coming off the box. So I could have shown that for completeness, and it would show they have to be the same. But I can say that 2by equals 2mg, so I know my by component is equal to mg. So now I have more insight into B aside from its relationship to phi. So I can take this, plug it back into the moment relationship, and now solve for B in terms of just mg and sine phi. And continue to crank that through and get the answer to the question that was asked. All of our mg's end up canceling out, and we can actually solve for an angle phi of 52.5 degrees that is now independent of everything else in the problem. So it's dependent on the problem geometry in terms of the width of the box and the length of the rods, but is not dependent on the weight of the rods per se. So this is basically just stepping through two different FBDs, one for a single rod and then one for the pinned assembly, and then plugging back into a moment equation. We were able to get this. So luckily no big math this time, but this was quite a geometry chase, so that's admitted. So that is it for this particular problem.